Welcome back to this next video in which we are proving that the alternating group on the set of n elements is simple that n is greater than or equal to 5. Okay, so we're now going to actually begin the proof. Okay, so remember we're doing a proof by induction. We know that the statement is true for n is equal to 5. We've now done the inductive assumptive step, and we're assuming that it's true for n is greater than or equal to 5 but less than k, and we want to prove that it's true for the alternating group on the set of k elements. Okay, so we're now proceeding by proof by contradiction approach, and we're saying, okay, let's suppose now that it is true for all of those ones less than k, but that it's not true for ak itself. Okay, so we're now saying that we have some normal subgroup of the alternating group on the set of k elements that is not the trivial subgroup or the improper subgroup. And what we now want to do is arrive at a contradiction. Okay, so what we're actually going to do, the strategy we're going to approach here is we are going to reduce this more and more and more. We're going to proceed by a bunch of lemmas. Okay, and each lemma is going to restrict this more and more and show what elements it cannot possibly contain. And eventually we will have ruled out pretty much everything, basically. Okay, so we're going to restrict this down, down, down. That's the approach that we're going to use. Okay, so we're going to begin then with what I will call lemma 1. Okay, and what lemma 1 is going to do is prove that actually this normal subgroup that we're assuming is non-trivial in the alternating group on the set of k elements cannot actually contain any element which fixes an element of the set 1, 2, 3 all the way up to k except for the identity element. Okay, so here comes lemma 1 then. Okay, right. So lemma 1 is that there cannot exist, okay, there cannot exist, which I'll write like so, there exists with a cross for it, okay, there cannot exist a sigma which is an element of our normal subgroup capital H, okay, such that sigma is not equal to the identity element, which I'll just denote 1, and sigma fixes an I, okay, sigma of I is equal to I for some I is an element of the set 1, 2, 3 all the way up to k. So for some I is equal to 1, 2 all the way up to k. Okay, so this is lemma 1, that this subgroup capital H, which we're assuming is this normal subgroup that we want to prove cannot exist, it first of all cannot contain any element which fixes a certain element of the set 1, 2, 3 all the way up to k except for the identity element. So this is effectively saying that with the exception of the identity element, H cannot contain a single element that has a 1 cycle in it. Okay, if you take its cycle decomposition, it cannot have a 1 cycle in, except of course the identity, which is made up of k 1 cycles. Okay, so this hugely restricts what can actually be in this normal subgroup. So this is part 1, if you like, of this restriction process until the point that we can prove this can't exist. Okay, right, so how are we going to prove this? Well, of course we're going to prove it by contradiction. So we will start with the assumption that yes, we do have an element of this form, okay, that fixes an element in that set 1, 2, 3 all the way up to k, and we're going to arrive at some nonsense. Okay, so what we'll do is say if there does exist a sigma which is an element of capital H with sigma not equal to the identity and sigma of I fixed at I, then what can we say next? How can we arrive at some rubbish from this? Okay, and indeed what we're going to actually show is that if this is the case, this subgroup, capital H, would have to be the entire group, the entire alternating group on the set of k elements, which is of course a contradiction because we're assuming that it is not the improper subgroup. Okay, right, so how are we going to proceed? Well, firstly, note that this means that if I was to intersect this subgroup H with the stabilizer of I, so I is now some fixed value, if this element sigma, it is fixing some I, we can find the stabilizer for that, gi here. If we were to intersect these two together, it's not equal to the trivial subgroup. Okay, because it would contain this element sigma, because sigma would be in H and sigma would be in the stabilizer of I. Okay, and therefore I can conclude that this intersection is not the trivial subgroup. However, I claim that I can also say that the intersection of H with the stabilizer of I in the alternating group on the set of k elements is going to be a normal subgroup of the stabilizer of I in the alternating group on the set of k elements. Okay, and the reason comes from the fact that H is a normal subgroup in the alternating group on the set of k elements. So let me draw a picture to explain why this is going to be true. Okay, so here let's say this is the entire group, the alternating group on the set of k elements. So I'll just colour this in here. So here is the entire group in green. Now, of course, we know that H is a subgroup of the alternating group on the set of k elements, so I'll draw it here. Again, we're saying a normal subgroup. That's part of the initial assumption that it was in a normal subgroup. Okay, so I'll colour it in pink here. And now I'm intersecting this with this stabilizer of I in the alternating group on the set of k elements. So here, let's have this as being the stabilizer of I, and I'll colour in that in orange here. And what I'm now trying to show is that the intersection of these two, which is of course this little box here, this is normal inside the stabilizer of I in the alternating group on the set of k elements. And I'll drop saying the stabilizer in this. I'll just say the stabilizer of I from now on, because it's a bit of a mouthful. Okay, so to prove this then, how can I prove this? Well, what I need to prove is that if I take any element, so for all G is an element of the stabilizer of I need to prove that if I use that to conjugate this subgroup, I get this subgroup back again, because this will certainly be a subgroup of that. The picture makes that obvious. Okay, and we know, well, the picture makes it obvious that it's a subset, but we know that whenever we intersect two subgroups together, we do indeed end up with another subgroup. Now, because we're working in a finite case, because everything's finite here, it is enough to show that whenever I conjugate an element of this subgroup by an element of the stabilizer of I, that I get something that's back in the intersection here. Okay, so it's enough to show that for all little h is an element of H intersect Gi, that if I conjugate little h by little g, I end up with an element that is back in H intersect Gi. Okay, and the reason for that is that little g is if it's an element of the stabilizer of I, then it's an element of the larger alternating group on the set of k elements. Okay, and if you use that to conjugate the entire group, never mind a subgroup of it, if you use that to conjugate the entire group, it will form a bijective map from the alternating group on the set of k elements to the alternating group on the set of k elements. Conjugation by each element of the group can always be interpreted as being a set permutation of the of that group. Okay, i.e. it's an injective map. Now, if I restrict it down then to this subset here, it's still going to be an injective map. If I can prove that all of the elements in here are mapped back onto that set, then I'm done. Because if it's injective and all of the answers are going back into here, then it must be bijective, because we're talking about finite set theory here. If you've got an injective map from here to, and you know that all the answers are going back into here, then it must be bijective, it must be surjective. Because if it's one-to-one, then the only possible way, because it's a finite set, is for everything in the codomain to have something in the domain that's being mapped onto it. So I can conclude it's bijective. I can conclude, if this is true, that all of the elements of the stabilizer of I, when they're conjugating H intersect the stabilizer of I, will give back H intersect the stabilizer of I. Okay, so why can I argue that this is true? Well, that's very easy. I know that capital H is a normal subgroup. Okay, G is just some element of the larger group. I know it's in the stabilizer of I, but that's just some element of the larger group. And of course, if I conjugate any element of capital H, which indeed little h will be, by some element in the larger group, any element in the larger group, I will end up with something back in capital H. So this is going to have to be in capital H, but of course little g and little h are also elements of the stabilizer of I, okay? Little g is certainly in the stabilizer of I, and little h has to be as well because it's in the intersection here. Okay, so if I just colour this in, little h is here and little g is here, or not colour it in, add it onto the picture. So when I conjugate little h by little g, it must also be in the stabilizer of I. So it has to be in both of these, basically. It has to be in the stabilizer of I because this is a subgroup and both of the things that we're composing here are in there. It has to be in capital H because capital H is a normal subgroup of the larger group, the alternating group on the set of k elements. And therefore, indeed, I can conclude this line here, that indeed the intersection here, which I'll just colour in yellow, is a normal subgroup of the stabilizer of I. Okay? Now, I know that the stabilizer of I is a simple group. It's isomorphic to the alternating group on the set of k-1 elements, and by the inductive assumption, that is simple. Okay? We also know that this intersection here is not equal to the trivial subgroup. So what does that tell us instantly? That tells us that H intersect GI must be the improper subgroup. It must be equal to GI, i.e. this picture is incorrect. What you need to do is get rid of all of this bit. GI must be completely contained within H. So what I can conclude is that GI is going to be a subgroup of capital H. Okay, so I was able to conclude all of that just from the fact that H contained a single element that fixed I, that the entire stabilizer of I is now completely contained in H. But it gets even better than that. I can conclude even more extreme things. Okay, right. So I know that capital H is a normal subgroup inside capital G, or not capital G rather, sorry, the alternating group on the set of k elements. Okay, I now know that the stabilizer of I, one of these stabilizers, for a certain element is contained within capital H. So I know that GI here will be contained within capital H. But this is just one of them. Okay, at the moment it's just the one that stabilizes this element that element sigma initially stabilized. Okay, what I can now claim, I claim that I can now say from this that all of these subgroups which stabilize elements are going to be in capital H. So I claim that from this, I can claim that G1, G2, all the way up to GK, all of them are contained in capital H. Not just one of them that was the one that stabilizes this one element that single element sigma stabilized, but I claim all of them are now going to be in there. And the reason is that we showed that we can turn GI into another one of these by conjugating it by a certain element. So in the prerequisite portion I showed you that if you conjugate one of these stabilizers by an element alpha, what you end up with is another stabilizer which will now stabilize alpha of I. Now because H is normal inside the alternating group on the set of k elements, then whenever I conjugate this stabilizer, this subgroup of it, by a certain element in the alternating group on the set of k elements, what I get must still be in capital H, okay, because it's normal, okay? And I claim that I can easily find you an alpha that sends I onto whatever you like. Okay, so I'll be able to find you an alpha that sends I onto 1, an alpha that sends I onto 2, an alpha that sends I onto 3, etc., all the way up to an alpha that sends I onto k. Okay, you'll always be able to do that, even in the alternating group on the set of k elements. I know we don't have the full flexibility of the symmetric group on the set of k elements, but still, hopefully you can appreciate that even in the alternating group on the set of k elements, you will be able to find a permutation that sends I onto whatever you like. You might have to have it sending other things all over the place, but that doesn't matter. All I need is a permutation for which I is sent onto a certain element. So I hope you can appreciate that, yes, I'll be able to find a permutation alpha to conjugate GI by to turn it into any of these. Okay, right. So that now implies, yes, that G1, G2, all the way up to GK, they're all going to have to be contained in capital H. Okay, so all of these stabilizers are going to have to be in capital H. I claim that from this now, I can go even more extreme. I can say that H is actually equal to the alternating group on the set of K elements. So how can I conclude that? When I claim that effectively all of these force this to be equal to this, okay, because I claim that you can build any element in the alternating group on the set of K elements by composing elements in these together. Okay, let me explain the reason. So we know that any permutation that's in the alternating group on the set of K elements can be written as an even number of transpositions. Okay, so there will exist a decomposition into transpositions for it. So I'll do this here. Tau 1, tau 2, where these are all transpositions, all the way up to tau, let's say 2r. So this is meant to imply that this is an even number here. Okay, so any element in the alternating group on the set of K elements can be written as a decomposition into an even number of transpositions. Now that's not much use to me like this, because these transpositions are not actually in the alternating group on the set of K elements. I would like to write sigma as a composition of things that are actually in here. These transpositions are not in here. They're in the larger group, the symmetric group on the set of K elements. Okay, so what I'm going to do is, there's a really easy solution to this. Just pair the transpositions up. So combine tau 1 and tau 2 to, let's say, make tau bar 1. Okay, and that then will be contained in the alternating group on the set of K elements, because it's one of its decompositions into transpositions will contain two transpositions, and therefore it would be an even permutation, hence it would be in the alternating group on the set of K elements. Okay, and so on. So you would also create tau 2 bar, okay, which would be tau 3 with tau 4, etc., all the way up to, you'd have tau bar, and then you'd have an R of these, because if you had 2R transpositions, then overall you'll have R of these things that you've constructed from two transpositions in this way. Okay, so I can write it then as a product of these things that are constructed out of two transpositions, and of course all of these are now in the alternating group on the set of K elements. Okay, so here's my overall claim then now. All the elements then in the alternating group on the set of K elements can be written then as a decomposition in terms of these tau bars, in terms of things that are built out of two transpositions. Okay, now each one of these, every possibility for tau bar, they're going to be contained within one of these stabilizers. So I've already said that all of these are going to be in the alternating group on the set of K elements. They are built out of just two transpositions, each of them. Okay? They cannot possibly move every single element, because remember, when we talk about the alternating group on the set of K elements, K is going to be greater than or equal to 5. Really, we want it to be greater than 5. So actually, I'll get rid of that equal to. It's going to be 6 or greater, okay, because we've already proven it for 5. I don't care about 5. So we're talking about the alternating group on a set that is size 6 or greater. Okay? Two transpositions cannot move every element. At the absolute maximum, they can move 4 elements. Okay, so they cannot move every element. So every single one of these things that is constructed out of two transpositions is going to be in one of these stabilizers here. At least one of the stabilizers. More, in fact, usually. If we're dealing with K is greater than or equal to 6, then at least 2 elements must be fixed by each one of these. Okay, so they'll appear in 2 of them. But the point is they appear in at least one of them, and therefore all of these elements are going to appear inside H. But I'm saying now that any element in the alternating group on the set of K elements can be built as a decomposition of these elements, which are all in there. Okay, therefore, because this is a subgroup, it must be closed under composition. By composing these things together, I can build any element in the entire group, which is the alternating group on the set of K elements, and therefore H must equal the alternating group on the set of K elements. So I hope you followed that argument, okay, that any element in the alternating group on the set of K elements can be built out of these elements which are made from two transpositions, all of these are going to have to be in at least one of these stabilizers here, and are therefore going to be in the subgroup capital H, and therefore capital H must contain any element of the alternating group on the set of k elements, because all elements in the alternating group on the set of k elements can be built out of composing these tau bars together. Okay, and therefore we have shown that this normal subgroup, capital H, is in fact the improper subgroup, which is a contradiction because we assumed initially that it was not an improper subgroup, the improper subgroup of the alternating group on the set of k elements. Okay, so what we have now done then is proven Lemma 1. We have proven that this non-trivial subgroup, capital H, which is a non-trivial normal subgroup, I've missed that word out, this non-trivial normal subgroup, capital H, cannot contain a non-identity element which fixes any one of the elements of the set 1, 2, all the way up to k. Okay, i.e., with the exception of the identity element, capital H cannot contain any element that in its cycle decomposition has a 1 cycle. Okay, so we've now hugely restricted which elements can actually be in this subgroup capital H. And in the next video, what we'll do is restrict it further, and we'll make our way towards restricting it totally to the point that it can't exist.